Chapter 3.2. Chapter 3.1 was about different types of averages. In Chapter 3.2, we're going to get into some calculation, and this is measurements of variation. Now, the root word for variation is vary. So this is how our data values vary from one another. There are three types of variation. The first one is what we call the range, and this is the difference between the largest and the smallest value. That's the easiest one to calculate. Now, notice I've put 2 and 3 on the same line. The second type is called variance, and the third is standard deviation. I've put them on the same line because once you've calculated one, you have both of them. Now, this is the measure of the spread of the data around the mean. So this is the relationship of your data values as it compares to the mean, or X bar, of your set of data. Okay, now here is the formula to calculate the sample variance. Now, if you remember, the sample mean is X bar. The sample variance is called S squared. Now, it looks a whole lot more complicated than it actually is. This reads the summation of X squared minus the summation of X to the second power divided by n minus 1. And here in a minute, we'll do that calculation, and I'll show you how to do it on your calculator. Now, the standard deviation is what we use in application most often. And the standard deviation is S. Well, how do you find S? You take the square root of S squared. So once you find the variance, you just take its square root, and you then have the standard deviation. Now, I have directed you to your book on page 96. On page 96, it shows the formulas to how to calculate the variance and the standard deviation by using what is called the defining formula as well as the computation formula. What I've shown you in your notes is the computation formula, and that's all I use. I think it's the easier of the two, so I restrict our discussion to only the computation formula. All right. Also on page 96, there is an example which is talking about the diameter of roses that might be used like in the rose parade. So it gives you your set of data. So to calculate the variance and the standard deviation, you want to create this chart or this table right here, and it will be extremely helpful. So right here I've listed all of our X values that were given in the book. 2 means a rose that was 2 inches in diameter, all the way to 10 means a rose that was 10 inches in diameter. So this is what was given, and there's a total of 6 values, so n is equal to 6. Then, because of my formula, I need X squared. So what I've done is squared each of these. So 2 squared is 4, and so forth. Okay. Then what I need is their summations, which just means add them all up. Okay, so if I add 2 plus 3 plus 3 plus 8 plus 10 plus 10, let's see, I've already got that in my notes. It's 36. So these add up to 36. And the X squareds adds up to 286. And these are the values that are going to be what we use in our formula over here. All right, so I've rewritten the formula, and S squared is sample variance. So what I'm going to do is calculate the sample variance. So S squared equals summation of X squared. Summation of X squared is 286. Minus, and this is where you need to be careful, this is the summation of X, which is 36 to the second power, divided by n, and there's a total of 6 of them. All of that divided by n minus 1, or 6 minus 1. Now, I'm going to show you how to put this into your calculator, so you put all the numbers in your calculator and you only hit equals once. The key is your parentheses. You'll start out with the set of parentheses here, and not again until after the 6, and then you need to put the denominator in parentheses as well. So let me get the calculator up so I can show you how to do this. Hopefully you will be able to see. So I'm going to do open parentheses. Oh, you're seeing a there we go. I'm going to do it best I can. You're kind of seeing a reflection, and I apologize. 286 minus 36 squared, so 36 to the second power divided by n, which is 6, then I'm going to close those parentheses, divided by, open parentheses, 6 minus 1, close parentheses, and now I only have to hit equals once, and I get 14. So s squared equals 14. And again, that is the sample variance. Then, if you were asked to find the sample standard deviation, you just take the square root of 14, which is 3.74. And hopefully you know how to do the square root on your calculator. So 14, sample variance. 3.74, sample standard deviation. Now, the s squared and the s is a statistic because it refers back to a sample. The parameters, which refer back to the population mean, which we'd already discussed, is mu. Population variance is sigma squared. Population standard deviation is sigma. So you need to be aware of x bar, s squared, s, mu, sigma squared, sigma. Those will be very important in our discussions as we move on. Now, we're going to do another example where you can do a comparison. This comes from page 94 in your book, and what you have is a bakery that is comparing suppliers that they get blueberries from. Okay, so they have supplier 1 and supplier 2. So what they want to do is compare the two to see if maybe I should only be using one supplier. All right, so that's what we've got here. Now, if you'll notice, I've already started the tables. Over here, my x values, I have 1, 2, 3, 4, 5. So they took a sample of 5. 17 means one box weighed 17 ounces, 3 boxes weighed 22 ounces from this supplier, and one box weighed 27 ounces. Then I went ahead and squared each of those numbers. 17 squared means 17 times 17, so there's 289, and so forth. Then we have supplier 2, and 1, 2, 3, 4, 5. We took a sample, whoops, not M, sorry about that. We took a sample of 5 from this supplier as well. 17 ounces is what one box weighed, all the way up to one box. Actually, they had 2 boxes that weighed 27 ounces. And then I've squared each of those. So now we are able to compare supplier 1 to supplier 2. So the first thing that I want to do is calculate their averages or their mean. That way, if one of them is consistently a larger mean than the other, then I'm going to go with that supplier. And remember, the mean is add all the x values and divide by however many there are. So let's do this summation. 17 plus 22 3 times plus 27 gives us 110. So to find that mean, I would do 110 divided by, there are 5 of them, and we get 22. So on average, this supplier gives me boxes that weigh 22 ounces. So then I would come over here, the summation of these, so I'm going to add these 5 numbers up, and what you'll find is it adds up to 110 as well. So 110 divided by 5, well, this supplier is giving me 22 ounce boxes on average as well. So then I want to see how do my values vary from one another. So the first type of variation I'm going to look at is the range. And that is taking your largest value, so this case would be 27, minus the smallest, which is 17. So it has a variation of 10 ounces from the largest to the smallest. So I come over here, and this supplier is also 27 minus 17. So it has 10 ounces of variation as well based upon the range. So right now they look a lot the same. So now what we're going to do is compare their variance and their standard deviations. So before I find the variance, I need to add these up. So I'm going to add 289 plus 484 3 times plus 729. And that adds up to 2,470. And then I'm going to do the same thing over here. I'm going to add all of these up, and they add up to 2,508. So there's something that's different right there, which means my variance and my standard deviation for these two suppliers are not going to be the same. So let's look at supplier 1, which is on the left, and we're going to calculate the sample variance, which is S squared, which is the summation of x squared, which is 2,470, minus the summation of x, 110 squared, divided by n, which is 5, divided by n, or 5 minus 1. And again, when you do this on your calculator, be sure that you put the parentheses in the correct place and then hit equals only once. If you do too much rounding several times throughout your calculations, you're going to get a skewed answer. So when you put all of that into your calculator, you're going to get that S squared equals 12.5. So that is your sample variance. So if we went ahead and found its standard deviation, we would take the square root of 12.5, and the square root of 12.5 is 3.54. Now, this is how your set of data falls or is a relationship with the mean. So the mean was 22 ounces, so it's 3.54 ounces up or down from the mean of 22. All right, so let's compare that to the sample variance of supplier 2. So we have the summation of x squared, 2508, minus the summation of x, 110 squared, divided by n, which is 5, divided by n minus 1, or 5 minus 1. And again, be very careful of your parentheses in your calculator. And when you put that correctly in your calculator, you will calculate that to be 22. So supplier 2 has a variance of 22. Supplier 1 has a variance of 12.5. So what that tells me is this supplier has more variation in relationship to the mean of 22 than this one does. Well, let's go ahead and find the standard deviation, which is S, which is the square root of 22, and the square root of 22 is 4.69. So supplier 2 is shown to have a higher variation than supplier 1. And what that means is the boxes from this supplier have a higher likelihood of being different than the mean of 22 ounces. And if you go back and look at the original sample, that proves to be true. So in this case, I might choose to only use supplier 1. So that's how you calculate the range, the variance, and the standard deviation. Next, we're going to look at what is called the coefficient of variation. Now, in the example we just did, we had two suppliers. We had boxes of blueberries, and their weight was calculated in ounces. Well, what happens if you have two different measurements? What if you're comparing ounces to, say, inches? Does 1 ounce equal 1 inch? Well, they're completely two different measurements. So what we do is we convert our numbers into a percentage, and we call this the coefficient of variation. And how we do that is you always take the standard deviation divided by the mean times 100. Over here, S is the sample standard deviation, X bar is the sample mean times 100. Here is the population standard deviation sigma over the population mean mu times 100. Okay, so let's apply that in a problem. It says the mean yearly salary of all the employees at Perfect Printing is $42,500. So notice here is my salary, which is money. There's the mean, and the standard deviation is 4,000. And the mean number of years of education for the employees, so years of education, on average or mean is 16 with the standard deviation of 2.5. Now, notice I used mu and sigma. Those indicate that my values come from a population. How did I know that? Because it said the word all. If it would have only taken a portion of the numbers, then I would have used X bar here and I would have used S here if it was a sample statistic. All right, so what we're going to do is calculate the coefficient of variation. So CV equals standard deviation divided by mean. Whoops, put too many zeros on there. Sorry. Times 100. And when you multiply it times 100, that's what moves your decimal point 2 places and makes it a percent. And you calculate 9.41%. So when I compare then years of education, because again, I can't compare salary to education. They're not the same unit of measurement. So what we're doing is converting them to a percent so I can compare them. So the CV here would be standard deviation. So in this case, the standard deviation is 2.5 divided by mean, 16 times 100. So when you do that calculation, you get 15.63%. Now, what that tells me is the years of education has a higher variability, which means those numbers are not as in close relationship to the average of 16 as these values are to its average 42,500. So that's how you calculate the coefficient of variation. The last thing that we're going to learn to calculate in 3.2 is what is called Chev's, and don't ask me who names these people, I don't know. Chev's theorem. And this is how the data is spread out around the mean for any distribution. Now, the reason it says any distribution, if you recall, the different distribution shapes are symmetrical, skewed left or right, uniform or bimodal. What this means is it works for any of those. So here's what it reads. For any set of data and for any constant k greater than 1, so k cannot be 1, the proportion of the data must lie within k standard deviations on either side of the mean is at least, and then it gives this formula. Okay, let me show you what you need to know for this. Say we are talking about 2 standard deviations where k equals 2. So I'm going to use this formula, and in place of k, I'm going to put 2. So I have 1 minus 1/4, which is 3/4, which is 0.75. So based upon that theorem, what it tells me is that 75% of my data fall within 2 standard deviations from the mean. So the mean minus 2 standard deviations, the mean plus 2 standard deviations. Then if we are to look at 3 standard deviations, so in place of k, I'm going to put 3. So I have 1 minus 1/9 or 8/9, and I get 0.8, which repeats forever. So they show that as 88.9%. So what you need to know is that 88.9% of the data is within 3 standard deviations. You don't have to have this formula memorized. You just need to know 2 standard deviations is 75%. 3 standard deviations is 88.9%. And then that brings us to, we look at 4 standard deviations, and then that's where we stop. So in the formula, I put in 4 for K, and I get 1 minus 1 over 16, or 15/16, which is 0.9375, which that's 93.75%, which they show as 93.8%. So again, what you need to know is within 4 standard deviations is 93.8%. Okay, so we're going to look at one last example. And we're going to apply the coefficient of variation that we learned, as well as Chevyshev's theorem. All right, in 1881, Billy the Kid killed 2 deputies and escaped from a jail cell in New Mexico. And then before 1985 renovation, they had a historian come in and do an analysis of the area, and they looked for artifacts, okay? So here's a sample that they took. So 1, 2, 3, 4, 5, 6, 7. So n equals 7. What they did is they have 7 excavation sites, and this is how many artifacts they found per site. So 851 means 851 artifacts were found in one particular excavation site. Now, what's nice is they already calculated the sample mean for us, as well as the standard deviation. We don't have to calculate that. So the coefficient of variation, if you recall, that's coefficient of variation is standard deviation, 266.84, divided by the mean, 566.86, and then you multiply it times 100, and this gives you a percent. So anytime you calculate the coefficient of variation, be sure that you put a percentage sign afterwards, and it gives me 47.07%. Also, let me mention at this time, sometimes that percentage can be over 100%. You might calculate 220% as a coefficient of variation. That's okay. It just means there is a high variability. All right. Then it wants us to calculate Chevyshev's theorem. Now, with this theorem, you're creating an interval, which means there's going to be 2 numbers. As soon as I see 75%, I think back to Chevyshev's, and that tells me it is within 2 standard deviations. So I know I'm going to do x bar plus or minus 2 standard deviations. So x bar is 566.86 plus or minus 2 standard deviations, which was 266.84. So we're going to calculate 2 numbers. 566.86 minus 2 times 266.84, and that gives us 33.18. That's the lower part of the interval. Then to get the upper part of the interval, you do 566.86 plus 2 times 266.84. And you get 1100.54. So this is 33.18 artifacts to 1100.54. And what that tells me is that 75% of the sites are going to have anywhere from artifacts from this many to this many. And that's a pretty high difference. It has a pretty high variability. All right, let's look at one more. And again, it's using Chevyshev's. We're creating an interval, so there'll be 2 numbers, and it says approximately 94%. Well, if you would recall, 4 standard deviations was 93.8%. That's approximately 94%. So this tells me it's within 4 standard deviations. So I'm going to calculate x bar plus or minus 4 standard deviations. So we'd have 566.86 plus or minus 4 times 266.84. So when you go to your calculator, you'll do 566.86 minus 4 times 266.84, and you get, and yes, it seems odd, but you get negative 500.5. 2, and now you're going to take 566.86 plus 4 times 266.84, and that's going to give you 1,634.22 artifacts. Now, you calculated a negative number. Yes, I would show that calculation. But in all actuality, you can't find negative 500 artifacts. So in the real world, this would be anywhere from 0 artifacts to 1,634.22. So that is chapter 3.2.